My talk is devoted to Feynman-Kac's formula for generalized time-fractional evolution equation. Such equations arise in models of anomalous diffusion. Let us say a few words about classical diffusion first. So, in the case of classical diffusion, basic objects are heat equations and Brownian motion. Namely, we can solve heat equation by means of Brownian motion using this nice formula, which can be called also a special case of Feynman-Kac's formula. And classical diffusion has two basic features, namely mean square displacement of the diffusing particles is proportional to the time increment, and the underlying processes have Gaussian law. Nowadays, there are many evidences that not only classical, but also anomalous diffusion may occur. What does mean anomalous diffusion? It is a diffusion under which at least one of these two features is not present. For example, mean square displacement of a diffusing particle is not proportional to the time increment, namely that the diffusion can be really faster or slowly as the classical one, and or the underlying processes are not Gaussian anymore. There are many examples in literature where we have anomalous diffusion in models in biology, chemistry, physics, and so on. So you can read this list if you stop the video and we go further. And of course, there are many models describing anomalous diffusion. And if we start with the so-called approach based on rescaling of continuous time random walks, we arrive to this equation. This is the basic equation of anomalous diffusion, and this equation is called time and space fractional heat equation. So Laplacian is replaced by fractional Laplacian, and first order time derivative is replaced by Caputo fractional derivative of order beta. Beta is between 0 and 1. And this equation can be rewritten also in integral form. So we again have fractional Laplacian as before. And in the integral form, this Caputo derivative corresponds to this integral operator, Riemann-Liouville type integral operator with this kernel of convolution type, and this is a power function of order beta minus 1. So this kernel here can be understood as a memory kernel, and this probably explains why the underlying stochastic processes are not Markovian anymore, and actually the solutions of such type of equations do not possess semigroup property. Nevertheless, there are some Feynman-Kac's formula known in the literature for such type of equations. Namely, there are some relations between such type of equations and stochastic processes. And so once again, now we discuss stochastic solutions. Namely, we discuss stochastic processes X such that this type of expressions provide solutions for such type of evolution equations. So there are two basic classes of processes which are used in the literature to provide stochastic solutions for such type of equations. First class is so-called Markov processes subordinated by inverse subordinators. So in particular for this equation number 1, as Markov process, we take a alpha stable Levy process which corresponds to fractional Laplacian. And as inverse subordinator, we take beta stable inverse subordinator, which corresponds to this memory kernel. But such type of processes, such type of stochastic solutions are founded also for a bigger class of equations. Namely, we can replace fractional Laplacian by just a generator of Markov process. And this particular kernel we may replace by any convolution type kernel, which somehow corresponds to subordinators to Bernstein functions, and hence to inverse subordinators. So such class of stochastic processes is used for not only for equation 1, but for some class of equations of this type. There is also another class of processes, so-called randomly scaled Gaussian processes. They look like this. This is a product of some Gaussian process with some random variable which is non-negative and which is independent from Gaussian process. So this random variable plays the role of random scaling. And for example, one basic example of such type of processes is the so-called gray Brownian motion. This is just this product, where as Gaussian process we have a fractional Brownian motion with a Hurst parameter beta half, and as a random scaling we have a particular random variable, square root of a of b, a with index beta. This is a random variable whose distribution has Laplace transform given by Mittag-Lefler function with parameter beta. So this stochastic process, gray Brownian motion, provides solution for equation 1 in the case when alpha is equal to 2. So namely for time fractional heat equation. But there are also another representatives of this class, randomly scaled Gaussian processes, which solves equation 1 also for all other alphas between 0 and 2. And so actually all randomly scaled Gaussian processes which have been considered in the literature so far, they all are self-similar with stationary increments, and hence they are good for modeling. So it is interesting to understand how far can we use this class of processes to provide stochastic solutions of time fractional evolution equations, and also what kind of relations exist between these two classes, why these two so different classes are used to provide stochastic solutions for time fractional evolution equations. So these questions motivated us to start our own research. This is a joint work with Christian Bender, and you can find the results of our research in our archive preprint, stochastic solutions of generalized time fractional evolution equations. One more paper comes soon. And so I have a few minutes to give an outline what happens in this paper. So we consider evolution equations of this form, where K is a memory kernel of a general type, so not necessarily convolution type. And L is a generator of a Markov process. So we have understood the structure of stochastic solutions for such type of equations, and we have understood the relations between two known classes of stochastic solutions, and we have found also some intermediate classes of stochastic solutions. So let me say a few words about the structure of stochastic solutions. As I said, L is the generator of a Markov process. So there is a Markov process Xi. And K, this is our memory kernel. So starting from the memory kernel K, we can construct a function phi, which is given by a power series where coefficients are depending only on time, and they are defined recursively only by means of our kernel K. So L provides us with a Markov process Xi, and K provides us with a function phi defined in this way. And if this function phi for each fixed t positive is a completely monotone function, then there is a corresponding random variable a of t such that its Laplace transform is given exactly in terms of this function phi. In this case, we can use this subordinated process Xi subordinated by the process a of t as a stochastic solution of this nice equation, generalized time fractional evolution equation. Of course, if this K belongs to the special class of convolution kernels, which correspond to subordinators, then as this process A of t, we can use corresponding inverse subordinator, but not necessarily. Actually, we can use any other process A of t whose one-dimensional marginal distributions are prescribed, actually given by means of this function phi. Okay, so this is the first step. Second step, in the case when our kernel K is time homogeneous, we can use instead of the process A of t, the process which looks like this, a particular random variable A multiplied with t to the power beta. So we have split it up randomness and dependence on time, and this random variable A is just any random variable whose distribution is given in terms of our function phi at time point t equal to 1. Okay, and further, so in this step, when our kernel is homogeneous, we can take a particular a of t in this way, a multiplied with t to the power beta. So we have this process as a stochastic solution, and we can go further. If our Markov process Xi is stable, then we can pull out this random variable a and create a random scaling instead of this random factor a in subordination. So as stochastic solutions, we can take either Markov process subordinated with this guy or a randomly scaled time-delayed Markov process. So this is a new class of processes which can be used for stochastic solutions for such type of equations. Let us consider a particular example, time-fractional heat equation. So the kernel is given by a power function. Then the corresponding function phi is given in terms of Mittag-Leffler function. One can just calculate it, define all the coefficients and calculate it. As L, we have a fractional Laplace, we have just a Laplacian, for example, 1/2 Laplacian, and hence the corresponding Markov process is Brownian motion. And hence, by our results, we can use a stochastic solution Brownian motion subordinated with respect to any process A of t, such that the distributions of random variables A of t are given by this function, Mittag-Leffler function. In particular, as one option, we can take inverse, beta stable inverse subordinator, and we obtain a known representation. On the other hand, our kernel here is homogeneous, and hence as A of t, we can use this product, random variable A beta multiplied with t to the power beta. And further, of course, since Brownian motion is stable, we can pull out this A of b to produce a random scaling. So we obtain then stochastic solutions as a randomly scaled, time-delayed Brownian motion. And further, Brownian motion, so time-delayed Brownian motion as here has the same one-dimensional distribution, marginal distributions as fractional Brownian motion with Hurst parameter beta half. So we can replace this delayed Brownian motion by fractional Brownian motion, and then we obtain another stochastic solution, which is just gray Brownian motion. It is again another known representation. So we have restored the whole line between two known representations, stochastic solutions of time-fractional heat equation, and our results, similar results hold also for in general case for Markov processes, but we also can replace L by L plus V, so we can add potential, so we can create Feynman-Kac formula. We can also consider L, which is just a generator of a strongly continuous semigroup or Schrödinger group, so we can consider also time-fractional Schrödinger equations. And also our approach allows to starting from a general kernel K, our approach allows to construct the corresponding function phi and hence the corresponding random variables A of t. In particular, for a big class of kernels given in terms of Appel's third generalization of the Gauss hypergeometric function. So this is a family of kernels with 4 parameters, A, B, mu, and nu. One can find the corresponding function phi, and this is actually the 3-parameter Mittag-Leffler function, or Prabhakar function. And for a particular choice of our parameters, A, B, mu, and nu, one can restore also 2-parameter Mittag-Leffler function and 1-parameter Mittag-Leffler function, and then the corresponding kernels reduced to power kernels, in particular the kernel which pops up in the governing equation for generalized gray-Brownian motion. So you can find these results and many further results in our archived preprint, and you are welcome to discuss all this topic in the live discussion during the conference. Thank you very much.